Manufacturing is changing fast. But how can new digital technologies like extended reality, telepresence, and speech recognition make the handling of robotics in factories smarter, safer, and more efficient? In the Vireo project, we set out to find out that. Training operators, designing robot cells, and controlling machines remotely are all complex, time-consuming, and sometimes risky tasks. We wanted to see if metaverse technologies could add value or change something in current workflows, perhaps even driving a shift in how we operate, create robotic environments, and manage training. Together with our industry partners, we built and tested practical solutions using XR, LiDAR, point clouds, and speech recognition. This all happened iteratively, allowing us to explore different options. Our goal was to create ideas that combine new types of interaction with existing infrastructure. In use case 1, we developed a virtual reality training prototype for ABB robots, where users can control different robots using the Omnicore Flex Pendant. A pendant is a handheld controller used to operate industrial robots. Jogging means manually moving the robot in small increments to teach it positions or test its movements, an essential skill for every robot operator. We created a system that takes information from Robot Studio, a robot simulation application for ABB robots, and streams the robot's rotations and locations to our Unity Metaverse platform, which is powered by Proverse. In this app, the operator or instructor can create tasks by placing down points for the robot, which is equipped with the spot welding tool. After that, training can start. Operators can safely learn to jog robots, understand coordinate systems, and practice real tasks without stopping production or risking safety. In the tasks, the operators will rotate and move the different parts of the robot through the defined points and avoid colliding with obstacles. Virtual environments are an excellent way to practice tasks like these, which require real expertise in actual factory settings. They allow for repeated, safe training without interrupting production. For smooth communication, we also integrated Lingsoft's speech-to-text and AI services to see how they function in these types of virtual environments. With this, communication is first transcribed and then automatically translated into the language the user has selected. This way, users can interact with the system in their own language, making training and guidance more accessible. During the process, we also explored whether we could use Siemens Process Simulate for robot simulation instead of Robot Studio, but linking that with our platform was not possible during this project. For use case 2, we explored remote robot control using telepresence and additional ways to use extended reality for jogging and moving the robot's digital twin. For this case, we worked with a FANUC robot and RoboGuide. Using conventional methods, basic remote pendant operation was already possible. However, the operator's vision was limited to a 2D camera, which doesn't provide good depth information. To address this, we wanted to place the operator directly in the environment using a digital twin and stream a LiDAR-based point cloud from the real workspace. The live LiDAR can be scaled and positioned in the desired position, which helps the user to superpose the real world upon the virtual world and give a better understanding of the real robot's movement to the virtual environment. This would allow us to test whether these views would be accurate enough for real decision-making. We also aimed to control and replicate the digital twin's movement from the virtual environment to the real robot. However, this experiment is currently on hold. Normally, the operator must manually use the pendant to control the robot or, alternatively, unlock and move the robot by physically guiding it. During our iterations, we explored how these actions could be handled in the virtual environment. The first method was straightforward, but for the second, we added a blue projection of the digital twin to highlight the desired movement and location, while the more realistic version showed the simulated movement from FANUC RoboGuide, which behaves exactly like a real robot. In addition to the above, we used a third operation method. It consists on creating a set of tool positions and waypoints which together form a task for the robot. These waypoints can define if the robot tool is active or inactive, and they can be easily edited by grabbing and moving them. Using Lingsoft's speech-to-text technology, the user is able to define an annotation for any waypoint, which can be useful for teaching purposes or to better understand the created task in the future. The tasks can then be saved by giving them a name either spoken using Lingsoft's transcription or typed in the keyboard, and they are added to a list from which the user can select which task to load, unload, or edit. By performing these tasks with a digital twin and then sending the movement commands, we could improve safety in the future and enable remote access to robots, such as from behind a safety fence. In the future, extended reality glasses could further increase efficiency in robot programming. During the project, we explored robot cell design as well. It became apparent that point clouds could be a key instrument for improving design workflows, for example, in Process Simulate. However, the tool itself couldn't handle very large point clouds, so our idea was to test in Unity whether they could be as beneficial in VR for understanding the real space as we thought. Point clouds are digital captures of the real world, and knowing where pillars and structures are within the factory hall is crucial when placing a larger robot network. Detailed point clouds demand significant VRAM because every point must be stored individually, unlike 3D models where surfaces are interpolated from corner points. To reduce VRAM usage, we segmented large point clouds into areas and created sparser versions of each. These were stored on the computer's hard drive, and at runtime, only relevant areas were loaded into VRAM, with distant areas loaded in lower detail. This multi-level segmentation also eased RAM to VRAM throughput issues. We further improved performance with a GPU-based shader pipeline that dynamically adjusts rendering. If frame rate drops, the system can lower resolution by culling points or removing those beyond a distance threshold. The pipeline runs fully parallel on the GPU and maintains read-write access to the full dataset, enabling real-time modifications based on user interaction by simply adding steps to the pipeline. These optimizations allowed visualization of very large point clouds even on hardware with limited performance. Unfortunately, this development would have required much further work, and we decided not to pursue it within this project. Finally, throughout the iterative process, we explored different routes which helped us reach our final outcomes. Thank you for watching.